Hi everyone, welcome to lecture 13. Today we are going to start on chapter 5, and then the next lecture, lecture 14, will end chapter 5. And this is probably one of my favorite chapters because it's one of those chapters where we can really see applications to real world, and so we can kind of figure out why we do certain things and why certain things react the way they do to hot, cold, or pressure, or anything like that. And so this chapter is going to be all about gases. Okay, so when we talk about gases, we are looking at an actual phase, right? We can either be in one of two phases, or one of three phases, excuse me, which is solid, liquid, or gas. And so for this chapter, we're going to focus on that last phase, that gas phase. And in order to look at elements when they're in the gas phase, we really need to talk about what temperature and what pressure they're at, because this all determines what phase our elements are in. And so this chart here displays elements that exist as gases at 25 degrees Celsius and 1 atmosphere. Now, we haven't talked about atmospheres very much, but just to give you a heads up, atmospheres are denoted with ATMs. So atmospheres are denoted with ATMs, and we'll talk about that in just a little bit and what it means and why we measure pressure with ATMs. Okay, so just know that that's ATMs, and obviously 25 degrees Celsius is our temperature. So in this chapter, we're going to focus a lot on temperature and pressure of gases. Okay, you'll also see that, obviously these are gases most all the time. So they're not highlighted on here because, or they are highlighted because they're gases all the time. The rest of them are basically solids. So we'll talk about that as well. So here are some of the common gases that are found at 1 atm and 25 degrees Celsius. And most of these are things that you hopefully are familiar with already. So things like H2 or N2, O2, O3, which is ozone, the molecular fluorine, helium, neon, argon, krypton, xenon, radon, etc. Okay, there's also some compounds that fall into this category, and these are common compounds that we use all the time, like CO2, NO2, sulfur dioxide, hydrogen iodide, etc. So these are probably the ones that we are going to revisit pretty often throughout this lecture. So when we talk about gases, gases tend to always have the same characteristics, no matter what gas we're dealing with. And the first one is that gases always assume the shape of their container, right? So if we're looking at the gases in the room you're sitting right now, we assume that they're taking the shape, they're filling the entire room. Okay, so if we took this bottle, which is full of gas, and release that into the room that we were sitting, we would assume that those particles would be so excited and would fly all over the place until they basically filled the whole room. Or if that was perfume, right, all the gas particles from perfume would sit there in a very condensed state, and then once we uncorked it, it would fill the whole room again. So we can always assume that gases are going to take not only the shape of a container that they're in, or the room that they're in, but they're also going to fill it completely. So they'll take the entire volume of it as well. Okay, gases are extremely compressible. And when I say that, I mean that we can take this gas here and we could push it all the way down if we had a plunger or a syringe until it would not compress anymore or be pushed down anymore. And that's because gas particles they kind of bounce around crazy, but we can take them and we can kind of compact them back down again. So gases are extremely compressible. Gases will mix evenly and completely when put in the same container. So right now the air you're breathing is not only oxygen, but it's also CO2, and there's nitrogen, and there's argon, and there's other particles that are floating in the air that you're breathing, and they're mixed completely. So we don't just take in oxygen. The other thing is that gases have much lower densities than liquids and solids. So gases are much lighter. And that makes sense, right? If we look at water vapor versus just flowing water, our water vapor is lighter. Okay, flowing water is going to be more dense. And if we look at flowing water, we know it's heavier. So the gases are always going to have lower densities as well. All right, so I keep talking about pressure, and so we are going to mention some of the ways we might denote pressure. But basically, when we talk about pressure, pressure is always measured by looking at how much force is being applied well, we look at our mass times acceleration for our force. So pressure is our force over our area. And we can measure it in a couple of ways. So just automatically get this in your head that anytime we see pascals or ATMs or millimeters of mercury or torr, these are the common ones that I use. You should think of pressure. Okay, all of these denote units of pressure. Now, this diagram here also shows how we can create some, let me erase these, how we can create some nice unit equation factors. And so what these say is if you're working in perhaps ATMs and you want to go to pascals, then we could say something like 1 ATM equals 101.325 pascals. Okay, and we can use that in our box equation to make that conversion. Or we could say that 1 ATM, and this is probably the one you'll use most often, equals 760 millimeters of mercury. Okay, so you can play with those numbers. Obviously, if 1 ATM equals that many pascals and 1 ATM equals that, you could also say, reverse it. So it works the same. Be prepared to make some unit equation factors. So now I keep saying this millimeter of mercury, and we're going to come back to this a couple of times. But basically, when we measure atmospheric pressure, we'll use this diagram over here. We do so by filling a tall column or glass full of mercury, tipping it upside down into more mercury solution, and then we measure this space and see if it gets bigger or smaller. Because what's happening is if the air pressure here is really strong, it'll push something up the column and make this space smaller. But if air pressure is not strong here, say we have a vacuum or we have something else which is pulling pressure out, then this mercury here will rise, and your mercury inside your tube will decrease, so your bubbles will get even bigger. Okay, so this is the typical way that we would measure the pressure of the atmosphere. And so we get this millimeters of mercury because we are measuring this normally in millimeters to see how far our pressure or how strong our pressure is. If it's pushing down, if it's pulling the mercury out, whatever. So millimeters of mercury is a way we measure pressure. You're also going to hear me talk about ATMs. Okay, and ATMs are atmospheric measurements. And so if we were to go to the coast and put a column of air a mile or 10 miles or 4 miles up into the atmosphere and measure the pressure, we would notice that as we go up into the atmosphere, obviously we know the air becomes less dense, and so therefore we have littler and littler pressure. So at 10 miles in the atmosphere, I have a pressure of 0.2 ATMs. At 4 miles in the atmosphere, you see it increases to 5 ATMs, which means that down on Earth here, my pressure is 1 ATM. We are 1 atmosphere standing at sea level. And so, again, you can see that as we go up into the atmosphere, we decrease in ATMs. As we're standing at sea level, we're 1 ATMs. And this 1 ATM is going to play an important role because most of the elements we're worried about are going to probably be either on Earth or we'll need to figure out their exact atmosphere, where they're located within that. Okay, we can also measure pressures in the lab by using what we call a closed tube or an open tube system. And basically what we do is we take a gas, let me see if I can, we take a gas and we're going to put, one of them you see obviously is called a closed system, and that's the first one there. Note it. Okay, so here you see it's closed, and here you see opening. And then we take this gas and we generally do one of two things to it. We can either keep this gas, this is fire, right? And then watch what happens to the gas inside. What might happen is that, if the gas heats up, it forms pressure going this way, and we might see this column come up a little bit. And this would be considered vacuum because there's no air pressure from the outside pushing against it. We could do the same thing here, and again, we might see this rise. But since there is nothing stopping it right here, obviously we would expect that we would also have ATM pressure pushing against it, right? So air from the outside pushing against it, this air pushing against it here. And so we could have a little bit of a different system than what we're seeing over there. Okay, and again, we're going to look at a lot of these, like the nanometers, this example here, as we go through this chapter. Okay, so that brings us, like I said, to our first real relationship, which is pressure and volume of a gas. Okay, so the relationship that I want you to know is that as pressure increases of the gas, then we have our volume decrease. Okay, so pressure increases, volume decreases. Okay, This is what we call inversely proportionate. And I'll write that here. So as one increases, the other decreases. And so let's talk about that, right? So if we are looking at this column right here, and we have gas right there, and we pour mercury into the system, and the mercury is sitting right here. Now, the only difference between these three columns, here's our gas, right, and here's our gas. The only difference between the three columns is the amount of mercury we poured in. And you can see that as I pour in more mercury, so from here to here to here, as I pour in more mercury, my gas right here decreases, right? My volume decreases. But the pressure on my gas increases. So here's more pressure, and here is our most pressure, right? So as pressure increases, my volume decreases. This is our first gas law that we're going to talk about. And we call it Boyle's law. Okay, these are two common representations of Boyle's law. With Boyle's law, we always assume that nothing is changing except for our pressure and our volume. Okay, so that means that we have a constant amount of gas, it's never going to change, and we also have a constant temperature. Okay, so the only thing again changing is our pressure and volume. So again, when my pressure is high, my volume is low. When my volume is high, my pressure is low. Okay, so they're inversely proportionate. There you see that again, inversely proportionate. Another way to create that graph would be to do something like this, right? So if we take the inverse of volume, which is 1 over volume, and then you can see that then we create this linear equation because we're taking the inverse of volume. But this is the normal equation that you should be able to identify for Boyle's law. Okay? So now with this, we get our first equation. Okay, so pressure and volume are going to be put into this equation, where we take our first pressure times our first volume, and we can use our second pressure times our second volume. Okay, simple algebra equation. So this means that if I know the pressure and volume of my initial gas, I can find one of these two variables if I know the second one of what my gas is going to look like at the end. So I can predict how my gas is going to react with this equation. Okay, let's practice. So you get something like this. It says a sample of chlorine gas occupies a volume of 946 milliliters at a pressure of 726 millimeters of mercury. What is the pressure of the gas in millimeters of mercury if the volume is reduced at constant temperature to 154 milliliters? So what I would recommend is just going through and underlining all of the numbers and units, and then determining what they are. So if I look at this equation, I have a number and unit there, number and unit there, and then I have a number and unit here. Okay. If we look at the first one, it's in milliliters. So milliliters, you should automatically think volume. So I'm going to put a V. Okay, we have another milliliters down at the bottom. So this one would be a V. And then here's millimeters of mercury, so here's a P. Okay, now you just need to figure out if it's your initial volume or your starting point volume, or if it's your end point. Okay, so if we have a sample of chlorine gas, which occupies a volume of 946 milliliters at this pressure, and then it says, what is the pressure of the gas? If we were to change that, right? So this must be our V1, and this must be our P1. And so this is V2. Now, if we go back to our Boyle's Law equation, it was V1 times P1 equals V2 times P2. If we look at that equation, you can see that we have this, and we have this, but we're missing this. So this is the variable that we're going to need to solve for. Okay, so I'll pop this up here. So again, pressure and volume are the things that we're working with. Here's my equation. Okay, P1 times V1 equals P2 times V2. We found that P1 was 726 millimeters of mercury, excuse me. My volume is 946 milliliters, my initial volume. P2, we decided we didn't know. And V2, we said, was 154 milliliters. So now basically, we can take my equation and rework it for my P2. Okay, which if we're taking this equation, all we have to do is take P2 divided by, and that cancels that out and gets P2 by itself. And what we do to one side, we do to another side. Okay. So we end up with P1 times V1 over V2 equals P2. Then we can just plug in the numbers. Okay, so for P1, we plug in 726. Okay. And make sure you link these. For V1, we plug in this one, right? Which is right there. We're going to take both of those times each other and then divide it by this one. Okay, and when we do, we come up with 4,460 millimeters of mercury. Okay, so the hardest part of this is probably just figuring out what your equation is giving you. After that, you can easily solve for the variable. Okay, which brings us to our next gas law. So our next gas law focuses on temperature and volume. Okay, and this one's a little different. So this one is what we call proportional, because as temperature increases, our volume increases as well. As we heat gas, it gets crazier, right? So those particles start colliding and taking up more space. So if you can see here, at a very low temperature, my gas kind of likes to huddle together. But as we increase the temperature, my gas likes to expand. Okay, so as temperature increases, your volume also increases. During this set of equations, we assume one thing, and that's that our pressure, which we dealt with in the last set of equations, stays constant. So here we're dealing with the same amount of pressure. The variable we're changing is the temperature. Okay. We call this Gay-Lussac's law, or Charles' law. Okay, so Charles' law says that volume and temperature are proportional. Okay. Some things that you need to know for this law. Again, your pressure stays constant, so we're not changing our pressure at all. Okay, temperature and volume are what we are concerned with. And then for this one, all of your temperatures have to be converted to Kelvin. Otherwise, this equation does not work. So if you're given Celsius or Fahrenheit in your problem, you make sure you use your conversion. Most of the time I will give you Celsius, and then remember Kelvin just equals our Celsius plus 273 Kelvin. Okay, and that'll give us our Kelvin. So here is our equation. This one looks different because they're proportionate. So it's V1 over T1 equals V2 over T2. When they're proportionate, they create that fraction. When they're inversely proportionate, then we take them times each other. So the last one was inversely proportionate. This one is proportionate. Okay? So this is a proportional graph, you'll see, obviously. So as my volume increases, so does my temperature. Okay, let's work one of these. So something like this. The sample of carbon monoxide gas occupies 3.2 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters? Okay, assuming pressure remains constant. So right away we see this, and this, and we need to figure out what they are. So when you see liters, you need to think. So when you see liters, you need to think fast. So here we have volume. So here we have volume, and it's our initial volume. Okay, we have a degrees Celsius, so I know that's a temperature, and it's my initial temperature. And then down here we have another volume. Okay, and then it says what temperature. So we don't know our temperature, so we know we're missing our T2. Okay. So again, okay, so there's our equation. We are going to know that we have 3.2 liters. Okay, our T1 we have to do something a little different with, right? Because T1 we had to take Celsius, which was 125, and add 273.15 to get our Kelvin. Okay. Then we also have our V1, which is, or I mean, excuse me, our V2, which is 1.54 liters. And we don't know our T2. Okay, a big question mark. So let's just plug all these numbers into the equation and solve. Okay, this is our equation. Again, I just reworked it to get T2 by itself. And then I plugged everything in. So V2 we know is 1.54 liters. My T1 is 398.15 Kelvin. And all of that divided by 3.2 liters. So my liters cancel out. All I'm left with then is Kelvin, and I end up with the answer of 192 Kelvin. So now we're on to our last one. Second to last one that we're going to deal with today, and that's Avogadro's law. Now Avogadro's law deals with basically how many moles we have of a compound, or how much of that compound we have, right? Because moles determines our number of atoms that we have. So with Avogadro's law, we assume two things. We assume that a constant or our temperature is constant, and we also assume pressure is constant. So we're not changing those two things. What we are changing is our volume and how many moles we have. You will see that this one here is proportionate. So as my volume increases, the number of atoms I have increases, which makes sense. And as my volume decreases, the number of atoms I have also decreases. Okay, so our equation is right here. V1 divided by N1 equals V2 divided by N2. Now, I'm just going to point out down here on the bottom some different ways you can think about moles, because I know moles are confusing. And so here you can see that we have 3 different compounds. So we could say that we have 3 H2s. We could say that we have 3 molecules. We could also say that we have 3 moles, or 3 volumes, which I'll get to kind of in the next lecture. Okay, same goes for here. We have 1 molecule, or N2, 1 molecule, 1 mole, or 1 volume. Okay, and same here. Okay, so again, Avogadro's law is looking at, as we increase volume, we also increase the number of atoms we have. Let's practice this one. Okay, so ammonia burns in oxygen to form nitric oxide, which is NO, and water vapor. How many volumes of NO are obtained from 1 volume of ammonia at the same temperature and pressure? So let me give you an equation for this. Right, so think back to those sentences I showed you on the previous slide. This one, the equation isn't even going to be necessarily a lot of numbers, but if I look at what they're looking at, so they are looking at how many volumes of NO, right? So here's NO, are obtained from 1 volume of ammonia, which is right here. Okay, so if I just look at these, I have 1 mole of NH3 and 1 mole of NO, right? Or I could say, in more complex, there's actually 4 moles of NH3 and 4 moles of NO, right? That's reality, but I've simplified it because we can take that and divide it by 4 and end up with 1 and 1. So for every 4 moles here, I got 4 moles here, but this time they're saying, well, you only have 1. So if I only have 1 here, then you know you better only have 1 there. Okay, and again, that's like constant temperature and pressure. So then we can just assume that it'd also be 1 volume. Okay, so let's revisit our gas laws. I like these images a lot. So Boyle's law says that okay, so Boyle's law states that as our volume decreases, our pressure increases. So you can see as we increase the pressure here, my molecules have a little space down here. As we decrease our pressure, like something like this, you can see that I have a lot more volume, I have a lot more space. Okay, so again, these two are inversely proportional. As one increases, the other decreases. Okay, and we call that Boyle's law. Okay. So P1 times V1 equals P2 times V2. Inversely proportional. Charles' law, or the other Charles' law, or Gill-Lucas law, right, says that in 1, as my temperature decreases, so does my volume. Okay, but as we increase temperature, then we also increase our volumes. things get really crazy. Okay, so we have a proportionate relationship. So it's P1 over T1 equals P2 over T2. Okay, down here, Gay-Lussac's law says that as we lower our temperature, our pressure is also lowered. Okay, as we higher our temperature, our pressure increases, which makes sense. So here we have P1 over T1 equals P2 over T2. I realized I just made a mistake, so this is supposed to be V1 here, not T. So we were dealing with volumes up on top, pressures on top. Okay, so Charles and Gay-Lussac's law. And then the last one we dealt with was Avogadro's law. Okay, and this one again, as we increase the number of moles coming in, we also increase the volume. So here we have very few moles, very little volume. Here we have a lot of moles and a lot of volume. So again, it's going to be okay, to know those laws, you should be able to work with them very easy and read equations and just plug in basically. Okay, remember that when working with temperature, you want it in Kelvin. The biggest thing I can say. If you forget that component, then you basically can forget a lot of things. All right, so if we take all those laws that I gave you, and we basically set them up to equal each other, we would come up with an equation that looks something like this. Okay, that PV equals nRT. So you can see that taking all of these equations, we've got our pressure times our volume equals our moles, we'll come to R in just a second, okay, times our temperature. Okay, this is what we call the ideal gas equation. So ideal gas equation means that if we take a gas and it's behaving like the perfect gas, then all of this should give us kind of a way to test what's going to happen with our gas. So I want to go back to our gas constant. So R is a constant, and we haven't really dealt with a lot of constants to this point. But basically, what R is going to be denoted like this. So we're going to say that R equals, we were just to set R by itself, pressure times volume over moles times temperature. So R is basically the combination of all of these things together. And so it has the notation of taking 1 atm, again, 1 pressure, times 22.41 torr, which is a volume, okay, the liters, and I'll talk about this in a second, over 1 mole, because you know N is moles, times our 273.15. So I've taken basically ideal conditions to figure out what R is. And when I do that, when I solve this equation out, I find out that R actually equals something like this. Okay, so R equals, and again, I just took this and solved it, 0.082057 liters times atms divided by moles Kelvin. Okay, so this is a constant, so we can always utilize that constant to plug into here as a variable. We know. Okay, the next thing is, if used correctly, these should help cancel out some other things that are in that equation. Now, when using PV equals nRT, for that R variable, and you saw this, which you haven't seen before. You've seen once ATM, and we use that one ATM because that's basically our standard temperature and pressure. Okay, we also use 273.15 Kelvin, 273.15 Kelvin, which is our standard temperature. So we assume gases they're going to behave ideally at these temperatures and at this pressure. Okay, so that's where we get this. One mole. We assume everything's 1 mole, so we just keep this as 1 mole. Okay, but we've never dealt with this before, this liters. So ideally, we would say that at all of these, at 1 ATM, 1 mole, and 273.15 Kelvin, we assume that that would equal a volume of 22.4 liters. Okay, so this is a standard volume. We can also then say that 1 ATM, 1 mole, would be within that 22.41 liters. Okay, so again, here's our ideal gas law, and with that, we can solve out some other equations if we're given several of these variables for one gas. Okay. And again, normally it'll be given to you, but this is what it is, so keep that handy. R is never going to change. Okay, so here, this one says, what is the volume? Okay, so we're looking for our V. In liters, I want V in liters. Okay, that occupies, they gave us grams, 49.8 grams of hydrochloric acid, and then we know that it's at standard temperature and pressure, which we just went over. Okay. So how are we going to work this? Well, the booger of this is that I didn't give you moles. Okay, we have our temperature, we have our pressure. We need to find volume. So if I look at my PV equals nRT, I have R, constant, I have temperature, I have volume, and I don't have volume, but I'm looking for it, and I have pressure. But I don't have moles, or so we don't think, right? But we've learned in past how to take grams and convert it to moles. So that is the first step. Let's figure out our N. And that way we can solve for that volume variable. Okay, so temperature, we know, is 273.15 or 0 degrees Celsius, which is standard temperature. My pressure was standard as well, so it's 1 ATM. Here's where I solve out my box equation. Okay, so I know that I'm given grams, which means I have to have grams down here. And I'm going to moles. Okay, so I have moles up on top. This number is the mass of HCl, which I took out the periodic chart. And then I can just solve it out, and I end up with 1.37 moles. Now I have my N, right? Okay, then I can just plug everything in. Now, if done right, you'll see that once you plug everything in, here's my N, here's my R, here's my T, here's my P. You can see that we'll start crossing out all of the units. And the unit that we're left with should be the one that we're solving for. Okay, so my answer then is 30.7 meters. Okay, let's try this one. It's a little different. It says argon gas is an inert gas used in light bulbs to retard the vaporization of the filament. A certain light bulb contains argon at 1.2 atms and 18 degrees Celsius, is heated to 85 degrees Celsius at constant volume. What is the final pressure of the argon in the light bulb in atms? Okay, so the one thing you need to know about temperature again is that we need to convert it. And in this one, we are given changing temperatures. Okay, so I'm going to give you another equation. That you should have seen before. Okay, this isn't a gas law or an ideal gas law because my pressure is the only thing that we're looking for, and we're given two temperatures, right? So here we have ATM, 18 degrees Celsius and 85 degrees Celsius. Then you should have gone for the equation that has pressures. Okay, so pressure is here, V1, V1, T2, and we don't know the pressure. Okay. Remember to convert your temperatures. Okay, to Kelvin, which is just adding 273.15 to each of those numbers. So we end up with something like this when we do that. And now we can solve my equation for P2. And we end up with this when we plug in my numbers and my final answer. Cross out my kelvins, I should end up with ATM, so 1.488. Okay, so that should be all today. We will continue with the gas chapter in the next lecture, practice those equations.